Thanks, Juan, for the small introduction. And this, we are going to have 3 talks this morning. This is the first one, so I'm going to start from basically I will try to construct the definition of PoRep. That is going to be then the main topic for the next 2 talks. And I would like to construct it starting from the proof of space. So basically, half of the talk almost will be more on proof of space, because it's important to understand this definition, since proof of replication construct on top of proof of space. Proof of space, I'll say a bit more about it in a moment, but it's just the intuition is we want a replacement for proof of work. We want something that can do the same security, but where the resource that we use is work and not storage and not computational power. And the next step, then, the motivation to step again forward from space to replication is that because we want to use useful storage, not just fill your disk with random data, but actually fill your disk with useful client's data. So, as I said before, a proof of space, the motivation was to have an alternative of proof of work. You can use the application of a proof of space are the same that we have for proof of work. So it can be spam prevention or consensus protocols. It was introduced in quite recently at Crypto 2015 by Stefan, and I lost him. and others. And basically, it's a protocol between a prover and a verifier. The high-level goal is that the verifier wants to check the statement. That is, the prover says, I'm filling my machine with some space. A way to formalize this is that we have these 2 phases. We have an initialization phase, where basically the goal of the initialization phase is for the prover and the verifier to produce this string S. It's the filler from the space, so it has to be long. Like if my parameter for measuring the space, the storage, we call it N. It has to be N storage units, N units. And instead, the verifier are just a small advice, a very short string. This communication has to be efficient. I'll go back on this in a second. And when we are done with this, we can have this execution phase to repeat every time. This is a real verification, the real proof somehow, where the verifier, just using this advice, can check that the prover is actually still storing persistently in time this long filler S, okay? So if you think about this this is time, what is going to happen is that we have this long, I'll say more in a second, this more heavier part that is initialization, and then through time I repeat this execution, prover and verifier repeat this execution phase. And through all this time, if the verifier is saying good proofs, so you can say yes to all the proofs. We are secure that the prover is still storing S through all this time, even between 2 executions. We have some efficiency requirement, so we want that the prover and the verifier during execution, they are efficient. A way to asymptotically measure efficiency is to say that they have to be polylog, so any power of a logarithm in n. This the efficiency in the sense of how many, in the sense of running time, just running time. And in this phase, since we want communication be small, we actually need to allow the prover in this phase to be at least linear. In general, can be poly n. So a bit more in a simpler word, in this initialization phase, the prover is not too efficient, okay? It has to be slower somehow. And to formalize the security proof, we speak about this anti-soundness that basically says that in the execution phase, a prover is bounded but using at most n prime storage. And this step, running time is somehow bounded too, then the verifier is going to see yes with very negligible probability, okay? You would like to have n equal to n, but it's basically not possible in practice. So we call this difference between what the prover is really storing and prime, and then the aimed one, space gap. And clearly, this is one of the measures of how good your proof of space is. In principle, you want a space gap very, very small. But in all the construction that we have, we see that this is as a cost. The smaller the epsilon, somehow the efficiency, both for the prover and the verifier, depends. It's less efficient. They are less efficient. So if you want to go home and design a good proof of space, the first thing that you have really to have clear in mind is that you have to make a proof of space that when this goes down, goes to 0, you don't pay too much. So the dependency, the efficiency dependency on epsilon, in principle, is log or any function that doesn't grow too much. It has to grow. It's impossible it doesn't grow, but it hasn't to grow too much. For giving you some practical numbers here, when the first proof from Crypto 2015, this epsilon was 1 over 500 something, so the 1 minus 1 over 500 something. So the prover could pass the proof and be considered an honest prover just storing 1 over 500 of the space it was required to store. So not a good in practice parameters. In 2016 at TCC, there is a result from Ren and Devadas. They actually improved a lot on this factor because we can see that with that proof we have a space gap of practical. I'm talking about practical parameters here of 1/2. And the first, so 1/2 of the storage. So I pass the proof if I'm saving half of the storage. Still good. The goal, especially in the context of using real data, the goal will be something very, very small. So like 1%, something like that. And there is a result from Eurocrypt last year, from Ben, that actually say that you can achieve that for almost practical parameter. You can go as low as you want. It's what is called a tight proof of space. And last thing I want to say again is that remember that unfortunately, in a definition of proof of space, we need to require that the prover during the initialization phase is at least linear. The running time is at least linear in n. So it can't be super efficient, okay? And otherwise, we have this rational attack. That means that the prover in the execution phase, if he has a very, very efficient initialization phase, what he can do during execution, he can simulate initialization again and fake space. So this is somehow an intrinsic limitation of this construction. Now I want to discuss a bit more about these two constraints. So here in adversary, we say, if you think a moment, this is basically a trade-off between space and computation, because I'm bounding my adversary on both sides, both the storage and the computation is bounded. So in order to avoid to go back of proof of work and having a prover that can save a lot of storage because it does a lot of computation, we really want to avoid that. We have to have a way in the real world, in the real application, to make this true always. So the prover, the dishonest prover can't go here, he has to go there, and it can't because we have a secure proof, okay? So it's very important to bound the computation of the prover. How can you do that in practice? So if you have a clock, if you have an application, a real-world application with a clock, what you can do, you can just put a time bound on the answer of the prover during the execution phase, okay? This is what we call the time model. And be careful that if you want to be in this world, you need to look at the parallel complexity of your prover. So it's not enough to say that he has to do these many steps. And a step, when I say step, you need to think about some elementary operation. It can be a call to a random oracle. It can be other elementary operation in which we measure the number of, the complexity of the prover. So in this world, in the time model, it's super important to look at the parallel complexity because it's natural to assume that everything that I can do in parallel, they take the same times. So if I have 10 operations, but I can do them in parallel, is equivalent to actually one operation in terms of time. The other two models that we have here is that I could just say, look at computation without time. Let's say I don't have, in my application, there is no way to time. I don't have a clock to time the answer of the prover. So I can use some limitation on the computation. It can be something that is just infeasible. So this is a number of running steps that is just, we believe, infeasible for computational bounded machines. Or you can have some physical hardware constraint on the prover. For some reason, the prover has to use this specific hardware and nothing else, and I know that in that hardware somehow the prover needs some times, or it can't do, for some reason, more than this step. So this is a bit, somehow, an extreme of the other. They are a bit difficult to use in the real world. This is the one that we actually use in Filecoin, and so you will hear more about this later. And then there is a third option that we tried to use, we can't use right now, so you will see why the problems. Nicola is going to give more detail, but is what we call the cost model with the rational prover. So now the goal is not to make T just unfeasible for time or other reasons, but I just want to make it too expensive for someone that is rational to really go there and do it. Before going to now finally proof of replication, just like there are many related definitions about proof of space, proof of storage, retrievability. I don't want to go, definition of all, otherwise we stay here all day, but just two quick things to, I hope, help to clarify. A proof of space is not a memory hard function. It's not because a memory hard function is something that requires storage just during computation. And a proof of space, especially here we are talking about persistent space, is something that allows you to prove that space storage is used through time. And then proof of space time, it's a name that is used for many things, but specifically it's used for a construction that is very related to proof of space, but basically remove the constraint on the prover to be linear, to be efficient in the execution phase. So I don't care the prover is efficient on the execution phase. So if you remember the drawing before, this is basically mean that my execution phase can be, in principle, as long, something like that, or like initialization. This means that clearly it's not a proof that you want to do very often, because it's slower than a proof of space, so you don't want to do it very often. But removing that allows you to somehow have a simpler construction. There is a specific one. I didn't put the reference, sorry, ask me later, I can point it out. This is just to, I hope, clarify a bit. And now we want to go to useful space, right? Because that's the goal. So if we talk about useful space, it means that we have real data coming from the verifier. It's not just expanding a seed, filling my space with something. I want this real data, and the first things the first idea that you have in mind is that somehow you want to the verifier be able to consistently check that you are storing the data. So it can be that the verifier just sends the data to the prover, and he keeps a small tag, like you can think about a commitment to the data, and then I randomly check that you are still storing the consistently with the commitment, the tag that I have there. This works to prove that we are storing it, but we have a problem here that this data, they can be compressible. And it's a problem in general because we don't have any space hardness here. So if I want to use this in the place of a proof of work, what's the resource that I'm using? It's not clear. It's even more complicated. This is even more a problem in the case of Filecoin, when the prover and the verifier can be the same person because the verifier is just someone in the chain and the prover is same, so you don't have a way to distinguish between identities in the blockchain. And then, of course, for sure the data can be compressible, so there is no space hardness at all. So how can you solve this? This means that basically, okay, proof of retrievability, this is important, but we can't give up this proof of space. So you want to compose the notion of before a proof of space with the proof of retrievability. How do you can compose it? Again, the first idea, it could be just to both of them. Okay? Here, the verifier sends the data, the proof runs both the initialization phase of a proof of space, and he has the data. And then I check both the data in a natural way, and I run the execution phase of my proof of space. Is this okay? Nope. For the same reason as before, because I can still compress this. So in some reason, okay, you are proving space, but you are proving space in a very inefficient way, because if I can compress this, this is the only things that give me space hardness. So honest players are going to use 2 times the space, but bad players, dishonest players, are going to compress this, so are using this. So I have almost 1/2 again. I'm back to 1/2 proof space gap. That's not the good situation. And it's even worse if you put this in the context of a storage provider. And I want to somehow use this also to guarantee some replication, some redundancy property. And imagine that the verifier is asking to the prover to store 2 copies. So this is now a cheating prover can always pretend to store 2 copies because it does 2 execution of the proof of space, but just 1 of the proof of retrievability. So all this space is saved. And the more, the worse here, okay? So what this teaches us is that a good solution needs to be a protocol that is simultaneously on the same space, on the same data, a proof of replication, a proof of retrievability and a proof of space. Okay, so this is how the definition of proof of replication born. Okay, so if you want to be a bit more technical, basically now the verifier sends this data. I have only one operation that is run. We call it the replication. I replicate the D, so I get this R, that is the length is N. It's in the place somehow of S. It's my filler of the disk, but it contains the data as well. And the verifier has just a tag. This can be an interactive or non-interactive process. If it's, and then I have the same idea of the execution before. So I have an efficient phase where the verifier can repeatedly query the prover to check that it's still storing a large fraction of R, and the R contains the data. And we have a third algorithm, if you compare this to proof of space, that is very important, that is extraction. I need, since my data are inside R now, I need to be able to go back and extract the data if it's needed. And clearly, we want this efficient as well. So a practical efficiency of this part is actually one of the main interesting open problem research questions that we have. So if we want to formalize the definition, the idea, the goal is that you want the post soundness plus some a K replication security. That means that if my data are divided, let's assume that the data now has 2 blocks, D1 and D2, I want that the replica has the same structure such that from each block I can reconstruct the data block, because this gives you immediately this replication property in the storage when you use it as in the storage provider setting. Unfortunately, this is not possible to achieve in a pure sense, because dishonest prover can always sabotage the replica. This is what in the PoRep paper that introduced these primitives is called the sabotage attack. Because even if I have this structure, what it can do, it can manipulate the replicant and store R2 plus R1 in the place of R2. And in this case, what is really happening is that, OK, this is a replication. I have 2 things, but I can't extract anymore my second block in the data just looking at this. I have to look at this. Saying another way around, if I lose this, I lose also the second piece of my data. Okay, so I somehow this redundancy of replication is destroyed. Okay, and there is no way to really there is no way to prevent this. A dishonest prover can always do that because it's doing this on its own data, right? And it's very hard to detect something like that with a check. So the idea here is that to use some rational prover, go again in the rational setting and say, you know, even an adversary that does this, so does this kind of sabotage attack, is not going to save more space than an attack that does everything but not the sabotage attack. So I'm saying that sabotage doesn't help you to save space, and it actually puts you at some risk because, as I told you before, now if you lose this, you lose everything, right? So it's not rational, it doesn't allow you, so you are not going to do that. In principle, proving this kind of property is a bit tricky because you in a formal way, you have to show that for any prover that does this sabotage attack, there is another prover, and for any adversary that does the sabotage attack, there is another that doesn't do it, and is equivalent. It can be painful, but thank you, Ben. He did all the hard work for us, and there is a shortcut to this that you can take your proof of space, just prove that is a secure proof of space, and also that is a proof of retrievability that is usually easier to prove than the former on a committed value, and you are done. So something about if you want to read more, this is like the let's say the technical tools that we have. Okay, so it's especially for this reason, it's super important, you know, proof of space, because even when you want to construct a proof of retrievability, a way to do is construct a good proof of space. That's why I think it's important to look at that. This is some reference, as the one said before. There are some technical reports and paper working progress paper of Protocol Lab, and there are the 2 papers from Ben. They are both available on the print, so if you want to read more about this stuff, it's here. Now we can do 2 things. I'm asking to the other speakers and to everyone. I can go a bit over pebbling, or one way to construct a proof of space that is pebbling based on graph pebbling, or I can give you the floor and you can go more in the practical of Filecoin problems.
How about this? My slides have some intuition on pebbling, and then if you want, we can go more in depth on how do we go about proving.
Yeah. Yeah, maybe you can do then a whiteboard session on that. Okay. Okay, so I leave it to you, or what?
What I'm saying is that I'm gonna, in some of my presentation, I will go very high level to that, and then if we, depending on how we feel, we can go into details, or we can do this as part of the workshop.
Exactly. So there are more slides on pebbling. If they're needed, they're here. Okay. Thank you.